So a while back I made this video where I showed off a gravity simulation that I made. But there's a couple of problems with it, and mainly the biggest problem with it is that it kind of runs like garbage. I mean, it can only handle like 350 objects until my computer just starts grinding to a halt, so I want to fix that. The first is I enabled GPU instancing on the material. Here I have a material called fast GPU, and that's what I use on all of my gravity objects. And as you can see over here, I have enable GPU instancing turned on, and this was literally just toggling on a basic check mark. So that's pretty good. Another thing that you can do is turn off cast shadows and receive shadows on all objects that you'll be instantiating. Or all objects that you want to have lots of. That actually improves performance by quite a bit as well. Now the thing which is a bit harder to do is multi-threading. Modern computers have many CPU cores. Some even have like 16, 32 even. Some even have 64. And Unity by default only uses one of them. So that's pretty bad. And yeah, so instead of having a bunch of objects, let's just draw 5 objects, right? So instead of having these 5 objects all calculate their gravity influence from each one of these objects, right? So normally you would go through all of the objects in the scene. So right here you would have an instance of a script which has the positions and masses of all of these objects, and you would use all of that data to apply a force on this object, and you would do this for each object in your scene. And this works. It's just kind of gets a bit messy, and it's really hard to do multi-threading with it like this. So a better way is having a game manager, right? And this way you only have one copy of the list of all game objects that you want to apply gravity to, right? So this game manager would would loop through each one of these objects and apply a force from to this object from all of these objects. Then it would do the same calculation for this one and apply a force to this object from all of these objects, and you just keep doing this until you run out of objects to do it, and then you do the same thing for each frame that you want the simulation to go on for. And so that's just the basics. What you can do is you can actually put all of this in a for loop, into a big for loop, and use the first, let's say, I don't know, the first 20 objects is done by one thread, the next 20 objects is done by another thread, and you kind of just segment these tasks for a single thread, right? And like that, you can just offload a lot of the work off of the main thread and onto a bunch of worker threads. And for multi-threading, I'm using Unity jobs. Oh, wrong tab. So for multi-threading, I'm using Unity jobs, and this allows me to have, so in my Gravity Manager script, I have, I'm using Unity jobs, and this allows me to offload a lot of the work to other CPU cores. And this just gives me a lot of performance. And let me show you how to do that. So you need native arrays. So when working with native arrays, you have to remember to release memory, and you just have to be conscious of that. Make sure to dispose of these native arrays right here later. So I have, first, I find all of my objects with a script called small gravity. And this script is going to be applied to all objects. All objects that you want to have gravity is going to have this small gravity script applied to it. And this small gravity script, all it does is it has a public float for the start velocity, a public float for the start rotation, and this allows you to apply a starting velocity, starting rotation to whatever object you want to have gravity, right? And all it does is it just gets the rigid body, applies the force in a wake, and gets the angular velocity. So this kind of acts like a tag for the gravity manager to know, yes, this object wants to have gravity, and it's going to take the rigid body from this object instead of getting the rigid body by itself. You find objects of type small gravity and add all of those to a list called grav, in my case. Over here, it's just literally some inputs, like timescale inputs. It's just a bunch of timescales, just a massive if block. To reverse is what I multiply gravity by. So if, like this, in real time, I can change whether or not gravity is negative or whether or not gravity is stronger, weaker. So that's kind of fun to play around with. But yeah, this stuff doesn't really matter. Then in fixed update, I'm doing this in fixed update, so I don't have like weird, because that's when you're supposed to do all the physics stuff. I'm not really sure if that applies here, but better to be safe than sorry. Yeah, so I iterate over the transforms, however many transforms I have, and I populate the native position array with all the positions, and I am making the results array to be equal to 0. I'm basically just clearing that out. I'm going to get back to the rest of this code in a little bit. I'm just gonna go over here. Yeah. So here is my parallel gravity array struct. And yep. Yeah, so here's my parallel gravity array struct, and it derives from iJob parallel 4. This is a built-in Unity jobs, and it allows multi-threading to be much easier to be implemented in C#. And I like it. It's not too complicated. I got this working in, actually took me quite a while, like 2 hours. But yeah, it's interesting stuff, multi-threading. So in this parallel gravity array, so yeah, I'm creating a structure called parallel gravity array. It has a fixed delta time, the gravity constant, and a reverse, just a reverse float. All of these are floats. Then you have a couple of native arrays. You need to say that the current position and current mass array is read-only, because setting data in them, and Unity doesn't like that. I think it's called a race condition and inconsistent results, and you don't want that. Unity protects you from that. It tells you you can't do this, which, you know, nice. It doesn't let you do stupid stuff. So yeah, you have to put read only, otherwise Unity will complain and throw an exception. So here, this method is iJob parallel 4 dot execute. This will be called, and here's my big gravity calculation, and yeah. So I have an int called size, and it'll be equal to the current mass a dot length. So I have these 3 native arrays. I have a size, and I iterate over the size. So I iterate over all of the current masses, and yeah. So this is already a for loop, by the way. So the way that iJob parallel 4, so this is already going in as a for loop. This I is your current index, right? So this is what I'm talking about multithreading. So index 0 to 20 could be handled by one core, index 21 to 40 could be handled by another core, index 41 to 60 could be handled by another core, and yeah, so that's yeah, so this is already in a this is already in kind of a for loop, right? Which you can allocate to different cores. So what this does is inside of this iJob parallel 4 for loop, I have another for loop going with the size of my current mass A. And current mass A and result and current pose A should all be equal to exactly the same length. They should all be the same length. So it could be any one of these arrays. I just chose current mass A because, I don't know, just randomly. So yeah, so inside of iJob parallel 4, this for loop, I have another for loop going, and that index is called j. Now, if I does not equal j, then I want to find out the results. Whenever I is equal to j, then you're calculating the effect of gravity on itself. So add the result of I, add this effect. So fixed delta time times my reverse, and this reverse allows me to change the effect, the strength of gravity in real time, times math.normalize. This is so that I'm just applying, I just want to find the direction in which gravity should be applied. That's why I have math.normalize. So yeah, current position at j minus current position at y times this, yeah. So current mass a at current mass at I times current mass at j divided by math.pow. So this squared, math.distance, the distance squared between current position I and current position j. So current position I, the distance between current position I and current position j squared, and yeah, that's the denominator. And yeah, so if I and j were the same index, so they were both corresponding to, let's say, the 0th part of this array, then the distance between them would be 0 because you're talking about the same object, and 0 squared is 0, and you get a divide by 0 error right here. And so yeah, this line of code is actually pretty important. So yeah, you have this iJob parallel 4, and yeah, so this will give you a result array. This will, yeah, so this gives you a result array that you can use to apply forces. And yeah, so here you populate the arrays with the positions of all of your objects and set the results in fixed update. At the start of fixed update, get all of the positions of the objects, set the result array to be equal to 0 again, so you don't have any weird glitches or unexpected results or compounding results, right? Then you have a parallel gravity array, which I'm just going to call paragrav array, which is equal to a new parallel gravity array. Parallel gravity array is right here. It's this struct. So this allows me to set all of my variables. So fixed delta time is just time.delta time. Time.fixed. Fixed. Oh, I can't spell apparently. Fixed. Time.fixed delta time. Don't know why that was not time.fixed delta time. That might have caused weird results. Hopefully that didn't make any bugs. It didn't seem like it did anything bad, so. Set the gravitational constant to the gravitational constant that I have defined up here, which is, this is the real gravitational constant, and I times it by a large bunch of large numbers, so that I don't have to deal with humongous mass values, because that's just, dealing with humongous mass values is just annoying, and I don't like doing it. Just dealing with extreme values, like extremely small values or extremely large values in programming, it's just always annoying. You're gonna have errors, and it's just better to keep things more reasonable. So yeah, that's the scaled gravitational constant. My current position should be equal to my position array that I have up here. My current mass should be equal to my mass, the masses of all my objects. My reverse variable, which allows me to, in real time, control gravity, the strength of gravity, should be equal to this. And my result array should be equal to result array, which is equal to 0. Then I schedule a job. And to schedule a job, you need to know how large of an array, if it's a I.parallel4 type job, then you need to give it how big of an array it is, and that's just the number of objects that I have that I want to apply gravity to. So I'm just using the number of transforms that I have .count. Here you actually have to put in how many batches will be done by each core, right? So this is what I was saying, like from 0 to 20 is going to be done by one core, from 20 to 40 is going to be done by another core, and you can put like a static number in here, like let's say 20, right? But that's kind of bad because it doesn't scale. So if you have like 100 objects, it's just better to have it like this. So I have system.processor count. So the number of objects that I have that I want to actually iterate over, divided by systeminfo.processor count, so the number of CPU cores that you have, and just bring that up to the nearest integer value. And so that's how many batches will be done by each core. And then job handle.complete. So this basically just says wait at this line of code until all of my CPU cores give me back a result, right? So I just immediately schedule the job, wait for it to complete, then I iterate over all of my I have a for loop which runs over however many objects that I want to have gravity. Add force vector free. What is this? Where is this? Oh yeah. So this is just a vector free. Yeah, so this is just vector free. It gives you so yeah, I'm iterating over all of my objects and applying the results. So my x, the amount of force that I have in the x direction, the amount of force that I have in the y direction, the amount of force that should be applied in the z direction, and I have that all in this add force vector free. And I go to that object's rigid body, do dot add force vector free, and on application quit, I just dispose of all of the arrays. I don't think I have to do this because all of the memory would anyways be freed up, but I'm doing this just as a reminder as practice to remember to dispose of arrays like this, just as I don't know, just good practice, I guess. I don't know. So when it does matter, I won't forget. Yeah, so that's this multi-threading complete. And this allows you, to have stupendous results. I hooked up a little spawner script here, and I'm just gonna set the spacing between them to be, let's put a reasonable, yeah. So this allows you to have many objects, and it works pretty well. Yeah. So with, I can increase the simulation speed, and this is like, this is 100x. Oh yeah, well, 100x is a little bit too much, but I can have, I can increase the simulation speed by like 64x, and I still get 170 frames per second with 100 objects, which is pretty cool. And like I said before, because I have that reverse variable, I can apply different, I can change gravity in real time. So right now I turned off gravity, and that makes it explode, basically. And I can make gravity negative. And so you can see that little cluster is breaking up now. I can turn gravity back on. And you can see stuff is starting to stick together. And let me increase the number of objects so you can see the value in multi-threading, for real power in multi-threading. And let's see. So I have 600 objects right now, and I am getting 400 frames per second, which is just great. This is like an insane frame rate. Like, if I were to do this with the old method, at like 350, I got like 12 frames per second. It was super slow. But with this method, it's just so fast with this multi-threading. Okay, yeah. So yeah, this allows you to have some pretty neat simulations. And yeah, I just turned off gravity. Bloop. Turn it back on. Make gravity negative. Make gravity weak but positive. Make gravity strong but positive. Make it weak. Make it strong. Make it weak. Make it strong. Turn it off. Make it weak. Turn it off again. And it's just fun to play around with. It looks so fluid and nice, and just looks nice. And it's just interesting to look at, and it's fun to play around with. You can have a spawner script to randomly spawn them around, but it also works if you just have like a bunch of objects in the scene. And so let me show you that. Where are my objects? Why is that 200Y? Whoa. Okay, no wonder I wasn't seeing them. Let's zero this out. Let's move this. Boom. Zero. At 50. Whoa. What type of scale was I working at? Let's just turn off the view for the directional light. I don't want to see that. Yeah. So you can have stuff straight in your scene. It doesn't need to be in a spawner, and everything is working correctly. They're rotating around each other. You can actually make them actually rotate around each other. Let's just unpack these, because I don't like seeing that blue. Yeah, so let's make this like a very... Let me just show you like a bit of a model solar system of sorts. So I have this, have that, have a start velocity in the x direction of, I don't know, 2. Is that enough? Let's see. Oh, it has a pretty elliptical orbit, but that's working, that's orbiting. And even if it's very small, it's still applying a very slight a gravitational pull on this object. As you can see that it's orbiting, like it's kind of shaking and moving around a little bit, but not very much. So you can have create a couple of planets, pseudo kind of planets. So yeah, right here, and yeah, so now it's orbiting. Control D. Let's create another one. Let's make it orbit a little bit less. And you can just start going crazy with this and start making an entire solar system. It's great. Well, let's just increase the simulation speed on this. So, even with two objects, you get some pretty interesting motion. Like, just three objects, I mean. I'm also going to show you my camera script for moving around and stuff in just a second. But yeah, just like that, you can create a couple of rotating bodies and make stuff orbit around each other. Oh, okay. I also have, and that's with this small gravity script. It has a public vector free for its start velocity, and that's, is that misspelled? Oh yeah, it's misspelled. Oh, yeah, whatever. Yeah, so here's my camera controller. You can just look at it. It's probably really bad. I wrote it a while ago when I was kind of sleepy. But yeah, just pause, look at it if you want. It's nothing special. Yeah, it's just a basic camera controller, which allows you to look at stuff in a pretty controlled way. A nice thing about this is that whenever I hold the letter R down, it allows me to go like 50x speed, which is nice for moving around stuff really quickly. I also have a gravity spawner script, which I showed you before. That's this spawner script. Let's turn this off. Let's just, yeah, turn off everything else. So this spawner script allows me to have two planets, two prefabs. One planet is gonna spawn more often, and another planet is gonna spawn less often, right? So, or gravitational objects, I shouldn't say planets. So it's gonna make one of these spawn more often, and another one spawn less often. And you can create these, switch up the size of this, and this is just a vector-free int. So you can make this like all on one plane by setting the y-axis to be 1. So it's going to create a 5 by 5 sheet of gravity objects like that. So yeah, now they're all on a single plane, and that looks kind of cool. And they just start orbiting each other. And this works like flawlessly. It's just a basic script, and it lets you create large amounts of objects kind of randomly, and yeah, allows you to do some and you can just keep if you have a button for restarting the scene, you can basically have infinite amounts of variations on your scene, and each time you can guarantee that it'll be 100% unique, or not guarantee, but it's probably gonna be unique. Wow, even at like 1, 2, 4, 16. This is 16x speed. 16x speed, still running at 150 frames. Wow. And so like this, you have a you can make stuff spawn on a plane, and yep. You can also make it spawn in a cube if you just set it to be like, I don't know, 4 by 4 by 4. And yeah. So the way that it actually works is that it spawns 4 objects in the x direction. Yeah, it spawns 5 direction. So 1 object in the middle. I think 4 in the x direction and 4 in the negative x direction. So if you have 4 in the for the size, it will spawn 4 in the positive x, 4 in the negative x, and 1 in the middle. If you have 1 here, it'll just spawn 1 object. Or it will spawn 0. There is a chance that it will spawn 0. Yeah, now it spawned 1 object. If you have 2, it will spawn many objects. I actually made it such that there's like a 10% chance that an object won't spawn. I'm making this go at like 100x speed just because I can. That looks so glitchy. Okay, this is 1x speed. Yeah. So there's a 10% chance that it will not spawn anything. And the way that you have this is easily, you do if random.range 0 to 11. And remember, when dealing with random.range int, this one is inclusive and this one is exclusive. So the highest this can random.range function will give out is a 10, even if I have an 11 here, which is, you just have to watch out for that kind of stuff. And as long as it's not 10, which there's a 10% chance that it'll be not equal to 10 exactly, then do this stuff, otherwise don't spawn anything and just leave an empty space there. I do this so that there are just kind of like little pockets of void in it, so it's not like super dense, 100% dense, but you can just remove this by by lowering this random.range. And yeah, so then you do another random.range. So there we go. So now there's a 1 in 3 chance that that a unlikely planet will spawn, and a 2 in 3 chance that a likely planet will spawn. And this is the instantiation code x, which is determined by size. This is my size array, public vector free int size array, and I also have an offset. So stuff, you can make things spawn very far away from each other, and this way you have like a good chance to actually like zoom out and like the simulation just won't go crazy immediately if you have a high offset. You won't actually see anything happening for quite a while until the objects start to build up speed, and that can look cool and for certain situations. So yeah, I added a bit of like an offset. So x, which is equal to negative size dot x plus 1 times offset, and this is plus your transformed up position, so you can move the spawner around, and it's not working in like world space, it's like relative space. So if you move it 1,000 units in the x direction, it will spawn stuff 1,000 units in the x direction. It won't spawn stuff always at the standard 0, 0. And yeah, so have your prefab, the location you want to spawn it, then give it quaternion.identity because I don't want it to have any specific rotation. And yeah, so this was just a little showcase of ways to optimize the gravity simulation that I had last video, that I showed last video. That's gonna be linked in the description. If you like this video, or if you have any suggestions, any recommendations, if you spot anything that I could optimize even further, easily, like to a limit. I'm not gonna write assembly code to optimize it. Like, I'm not insane. But yeah, if you see anything simplified I can do to give an extra boost to your performance, write a comment, let me know. If you have any recommendations, just, yeah, let me know. And yeah, thanks for watching. Bye.